So before I get started, I usually like getting a baseline for my audience. So how many of you are Spring developers? Okay. Normal just Java, maybe some other web development. Um, okay, fair enough. Maybe Drop Wizard or something of that sort. Okay. Yep, there we go. Okay. I know get somebody. I did a lot of so I come in peace. I may come from machine learning, but I did Spring, I've did Drop Wizard, I've done a lot of web services. I'm more actually on the software engineering side than I am the machine learning. I mean, I do a lot of machine learning because I have to. It's like, it's like big data, whatever. But I kind of like I more empathize with the software engineers who are actually building the products and actually making revenue for companies, actually delivering the value. So I come more from the production system side. I did Spring for a long time, and then kind of leaped into big data, and I kind of ended up in this strange hybrid space between kind of big data, HPC, and Java. So what I'm here to talk to you, so I have this kind of strange perspective on what I like to call a microarchitecture for machine learning. So what I'd like to do is draw some parallels between data science, big data, machine learning, and software development and microservices, and kind of present like a software engineer's perspective on what production data products should look like, actually. A bit about me. I'm an O'Reilly author on an upcoming book called Deep Learning, A Practitioner's Approach. It's 250 pages on basically something that only has been held in papers until now. You get a guide on basically like how to do optical character recognition or object recognition or sentiment analysis or whatever kind of use case you have for what's called unstructured data or data mining media, basically. So these algorithms are great at automatic pattern detection in unstructured data. So we have a 250-page book, mainly based on Hadoop and Spark, for doing this thing called deep learning. That will not be the bulk of tonight's talk. This is kind of like my current venture, so to speak. I run a startup called SkyMind that does Hadoop and Spark-based deep learning, open source Apache licensed, very similar to what we are used to as Java developers. So fits kind of right into that mold. And then I kind of fit in this strange, like, again, like I mentioned, like HPC space, which is like Java with GPUs and Spark. So it's kind of this weird mix where I use special hardware and help hardware companies and finance basically do data mining on fraud and Internet of Things, streaming analytics, which we know Java dominates at. So what I'm here to talk to you about today is microservices. So, all right. So I had to. Sorry. Okay, let's get it out of our systems. All right. So, sorry, I couldn't resist. So we have big monolithic systems, right? So typically, systems through technical debt or what have you get like this, right? So they're pretty big, and eventually we want to kind of split this up into, kind of smaller subsections, right? A lot of big companies and production systems, I'm sorry. Anyways, a lot of big companies and production systems, you need to split up the work because there's a lot of teams working on a lot of different pieces of software, right? So how many of you develop with some sort of microservices architecture? Mainly, okay. So probably, is there some monolithic Spring XML in here? We're all still on Spring 2, right? Or is it 3 now? Okay, maybe we've moved on by now. But the bulk of my Spring was in 2 and 3 when I was doing it. But a lot of monolithic XML. Java. They kind of move towards annotations, right? But it's still kind of hard. Inversion of control systems are great, but there comes a point where you want to split it out a bit. You want to make it more maintainable, right? So kind of what I'm trying to here to do today is kind of talk about, like, I'm going to give a little mini intro to machine learning as it relates to ETL and data. So, so we'll talk about basic use cases, understand why this is actually an interesting space to be in, and why it might not be hard to maybe just dabble in it a bit, if you're not, if you're afraid of the math and that kind of stuff. I just want to show you it's not that intimidating. But again, focus on a software engineering, a new kind of production-oriented view of big data. Because a lot of, you hear about data scientists, They're typically glorified statisticians, basically, right? And really, I mean, and I'll address why later, but there's not a lot of emphasis in practice on good, clean code. People try to teach that, but it's not necessarily like it's not a thing for them. They're thinking more about, oh, I got my alpha and beta distributions, and then the user fits this model in some form. Like, that's just the way they think, and they don't think about production code. But in reality, you need both sides. So what I'd like to do is kind of like, I'm going to jump back and forth between both worlds and kind of show you, like, okay, here's what you're used to. Here's the parallel in data science. And here is why this is a problem. And here's why you should care about this now rather than later. So that being said, like, there's trade-offs, right? So if we think about monolithic apps, you have startups. Startups start like this. They just want to get something out the door, right? They're not thinking about how do I scale this. They're thinking about how do I survive tomorrow, right? So they're going to prototype in Ruby on Rails. They're going to prototype in Python, right? So there's this whole software development lifecycle that's based around, will the business exist tomorrow, or am I ready to scale a team? And the software engineering concerns kind of derive from that, correct? A lot of you probably work at various size companies where the concerns are going to be completely different. If you're in a big company like Netflix or Google or what have you, they're more focused on how do I write clean modular code that scales? How do I use existing libraries and make sure that two teams communicating don't clash with each other? How do I, Google is 2 billion lines of code. That's a lot, right? There's a recent Wired story that quotes that. Feel free to Google it. Basically, 2 billion lines of code, right? That's as big as it gets. But that's not unrealistic, though. I mean, big code bases, especially, are typically written in Java, though. I mean, you have whole Spring applications that have probably been around in banks for years now. Java is still being updated. It's not COBOL, thank God. But there's still this kind of this legacy big code bases out there, and there needs to be a different standard. There's a different standard in the Java community versus something like Python or Ruby, where there's a lot of prototyping. You kind of have this whole culture of dynamic typing, right? A is equal to 2. A is equal to hello. I don't like that. Like, that drives me crazy. Like, why do I not know what this is? Why can't I have multiple return types from a function, right? There's this whole mentality that, oh, but just docstring it. No, I want my compiler to do that. So there's always these trade-offs. Startups typically write in dynamic languages, and then as they scale, they move to statically typed languages, because the compiler helps them validate, oh, I don't have to run this gigantic piece of code, right, to know what it's doing. Like, it's a lot more readable. There's a reason Java code written 10 years ago still works today, right? It's because they focused on maintainability and backwards compatibility, while still incrementally adding new features such as lambdas and 8 and all these other things. They try to make the language better, but they take what works and is what's been established in some of the more cutting-edge languages, and they bring it back into the enterprise world. And we see gradual adoption of certain features. Realistically, Java 7 won't actually be out of date for another couple years yet. I'm still going to be using Java 7 for a long time, probably. That's usually the way it works. But eventually, we get new features. But again, over time, code I wrote 10 years ago will still be backwards compatible today, right? Or forwards compatible, backwards compatible, whatever, right? That is not true in Scala. Scala, as awesome of a language as it is, like everybody knows about the 2.9 to 2.10 kind of, like, so I don't know if, I like Scala, but I don't know if I can trust it. I can trust Java, right? So there's this whole mentality, though, about different languages, different kind of stages of a business. So again, monolithic, Ruby on Rails apps, maybe legacy enterprise apps, to this new microservices approach. And what I'm going to talk about today is kind of scale, and in this case, different stages of a business with the software development lifecycle. So in short, it starts small. You have your prototype. Your startup, you don't know if your startup's going to survive tomorrow. You're just going to see if this thing can get customers. So you create a login page, maybe a landing page. You throw some Google Analytics on it, and you hope it catches fire. And then if you have users tomorrow, then you have an early minimum viable product. But then all you're doing is moving fast and breaking things. So that is the traditional mentality in Silicon Valley. Facebook just changed their model, I think, what, a year ago maybe, and they've been around a long time now, right? So there's kind of this early mentality, right? And what I want to do is I want to address this, and then again, like the interesting part will come later when I actually come back and draw these same parallels in data science and machine learning, right? So what I want to do and demonstrate is that both software engineering and data science are driven by the business. They're driven by some end goal that your manager has, and or your team's goals, right? That are usually like you're a profit center somewhere, and you're writing the payment module, you're writing the new ordering form, right? Or you're writing the scalable microservices that's going to handle all your company's transactions, right? That's all driven by some sort of profit that you get paid, with a salary, right? You might legitimately be interested in writing those kinds of systems, but at the end of the day, software development is about making a living. It's about practical applications, right? So the software engineering practices are therefore reflective of the stage of the company it's in. Eventually, we get to a mid-sized company. Now we want to scale all the things, right? So, now we want to okay, now we're a team of 15 people, and now we're starting, we know we're going to be around tomorrow. So let's think about cleaning up some technical debt now. Let's think about how to get kind of into the next stage of my startup, right? I'm going to think about how do I grow this. I'm not worried about just surviving. I'm worried about growing this company from 15 to 100 people. So my software engineering practices are, again, going to be reflective of that, right? And eventually, then we have too many cooks in the kitchen. So now we kind of have this opposite problem where now there's a lot of people. There's 1,000 people. And all of them are working on the same code base, right? So this is where, and so this is kind of where microservices starts to come in. Once you've gotten to this scale. I know some startups have adopted it. Maybe they have really good DevOps people that know Docker, and they know how to do it without breaking everything. Unfortunately, microservices is too hard for most startups, and they don't have the bandwidth to think about how do I do this right. So you kind of get to this point where now you need to manage team complexity, people complexity, communication, right? So from here we need to think about, well, what are the trade-offs? Microservices is an amazing idea, and I think the idea of small modular components where basically there's a separation of concerns, right? So I don't know if you guys have done aspect-oriented programming, but that's kind of where it comes from, right? We all aspect J and all that, so I had to deal with a lot of code weaving. Oh man, there's still good ideas there though, right? So microservices has their trade-offs, and it depends on the approach of the company, right? So from here, do what's right for your product, right? So the key takeaway here is if you have if you have a goal, think about what that goal is. Whether you're building a data product, whether you're building a high risk application, like a banking application, maybe something that handles transactions. You're going to take different precautions and different practices relative to the end goal. So do what's right for your product. If you have, there's nothing stopping you from, say, prototyping in Java. If you have a team of Java developers, do what you're good at. If you already all know Spring Boot, use it. Most people tend to, a lot of founders tend to be beginning coders. So they don't necessarily, they're gonna take what they learned in Hack Reactor or Coding Boot Camp, and they're gonna go start their startup. That's their traditional story, unfortunately. And then there's more experienced teams who might know Java, or they came from Google and they know how to do things, right? So there's varying levels of development, but at the end of the day, do what's right for your product, and always keep the problem in mind, especially when you're doing any kind of software engineering. So this is where I'm going to be. This is where I'm going to be spending a lot of my time, is in data science and machine learning. And what I'm going to kind of do is, since we already know these basic concepts of software engineering, we all work at we work at companies. We know we've seen big companies, and we kind of know what they're dealing with. What I want to do is kind of educate you guys on some of the basics of machine learning from a software engineer's perspective. You'll get kind of an overview of that. And what we're going to do is we're going to draw parallels between that and software engineering. And then what I want to do is go into ML architectures. So that's kind of where the microservices comes in. So machine learning oriented architectures. And what I want to do is show that actually data pipelines and extract, transform, load are actually some of the biggest components in data. So there's actually a huge need to understand good software engineering practices when you're doing machine learning or any kind of statistics. So how many of you, so it's okay. How many of you have dealt or seen machine learning before in some form? Really? All right. So that's enough though, right? So this will still be interesting for you if you don't know machine learning, because this is going to get gradually harder, and eventually we're going to be talking about microservices and GPUs by the end of this. So it ramps up quick. So everybody will get something out of this tonight, I think. All right, so let's start with this data science and machine learning. So what is a data scientist? So we think this, but not really. So there's this kind of meme in the data science community where some people really are good. Some people really are that. Most people are not. Most people will just put data scientists on their resume and they only know SQL, which there's no harm in that. But you kind of have to. It kind of conflicts the field a bit, and there's not clear boundaries between who does what and when, and what team they end up on. So everybody says they're a data scientist. So you kind of have this. So what I want to drive home here is that data scientists vary. There's a whole range of them. Some people you have data engineers, and you have data scientists. Data scientists typically know Python or R. And they know what a beta distribution is. They don't know what a REST API is, or they don't know what a MVC is, right? It's two completely different worlds. But in reality, all of these are a part of a product. The more of the stack you understand, even if you only have an elementary understanding of what the other guy does, it at least allows you to stay productive and be able to work and interface with the others. So in this case, what data scientists typically do is they actually, if you do get these hybrids where they know some stats, maybe they had a math degree, maybe they did a master's in stats, so they know the basics. They know what a beta distribution is. They know what a chi-squared test is. They know about variance. They know about means. They know about different ways of manipulating data. One thing and if they're good enough, you can never tell when they're telling the truth. Right? So if you think about it, you never know when they're telling the truth because they can always distort that data visualization you're looking at. All they got to do is change the scale of the numbers, and all of a sudden you look profitable, right? Or maybe if I'm growing 30% month over month, but I've only been around a week, they're not going to tell you that, right? So they're going to do. So the data scientists, the good ones, are the ones who make their charts look good. They're the one that make the business intelligence metrics look good, right? So they might have this skill, but if that guy who knows how to make the profits look good can do software visualization and maybe D3 or front ends in JavaScript, they're a valuable asset to the company because they're going to be doing everything. They're going to be the boss's personal assistant, being like, hey, I'm keeping an eye on you. I need to look good, right? There's going to be a lot of that. So these people are clearly valuable, and their salary reflects that. There's this other side where you have maybe some software engineers who maybe know machine learning. So maybe they got some basic understanding of it, and the main thing they do is distributed systems. So those are the guys who do stuff in Java. It's a lot of Hadoop and Spark. And what they try to do is basically build the data pipelines. So whether you know it or not, a quote-unquote data scientist, the first data scientist is actually a data engineer. Because what they do is, before you have a data infrastructure, you have to have data warehousing. You have to synthesize your data. You have to set up the infrastructure. You might not deploy Hadoop right away either. You might just do Redshift, Postgres. You need to be able to assess a data architecture. That's a software engineering characteristic. You're not going to deploy Hadoop. As much as I'd like to sell that vision, because that's what I do is I sell Hadoop, right? I work with Hortonworks and some of these other guys. And we help Hadoop vendors with certain problems. So as much as I'd like to propagate that vision, it's not necessarily true. You're typically starting with a relational database, and you need to be able to assess, when is my kind of scale of data ready to move up to this next step? When am I ready to hire a team of data scientists when I have data to actually monetize, right? Oh, Chris, I wanted to ask, what is the protocol for a break? Like, do we do one, I don't know, like, do we go straight? OK, just keep going? Awesome, OK. I'm fine with that. I'm fine with that. OK, I'm fine with that, trust me. I just want to make sure there wasn't like some protocol I didn't know about. OK, I can keep going all night. All right, well, let's go. I can go till 9 o'clock. All right, just making sure. Anyways, so if you need to walk out, feel free. Anyways, so that being said, so there's the guy who lies, and there's the guy who builds the infrastructure for the guy who lies. That's kind of what you got. So you got, that's what it is, right? I mean, it's some guy who manipulates data and turns a profit for the company. Like, data scientists are hired after you get the infrastructure to lie about the data, right? Or, maybe you're solving some real problems. Maybe you are saving the company money. You're doing fraud detection. You're doing something that really matters. Like, you have some data. You have a high amount of it. Maybe you're doing real-time sensor data. Then you need to be able to spot the trends. So there's kind of different skill sets in machine learning and data science. There's this kind of infrastructure, and then there's this and then there's the guy who's really good at math. And then there's the guy, and then you got the guys at like Google and Facebook who are in the ivory tower who just write the papers. Those guys are off somewhere else. They don't build products. So most of the industry is kind of this weird. There's kind of this data scientist, data engineer, some guy in the middle, who might know a bit of both, or maybe they do both. Who knows? If you've done enough for a few years, you never know, right? So that being said, the main thing that data scientists do, a lot of it is A/B testing. Did this button increase my revenue? If it's green, do I get more profit? So they ask these kinds of questions. So they do a lot of interface testing. So big companies will hire swaths of data scientists whose sole job is to make sure that somebody clicks on that right ad, or that call to action gets optimized, right? So that might be an abstract concept, but basically what they do is they say, OK, we're gonna split our user base into two halves. One of those will click the green button. Another one will click the red button. If the green button got more clicks, we're going to use the green button. So it's called a split test. So this is typically for optimizing websites. So you optimize individual. So what you do is you hold out a portion of your website, right? So a portion of your website might be a new landing page. So so there's actually some serious software engineering that goes into, depending on where the user's IP is, route them to this address, or route them to this page. There's actually some serious software engineering that goes on there. There's a lot to do with REST APIs, JSON endpoints. It's a lot of the data science world is JSON, actually. So there's a lot you have to know about REST endpoints. So you have to, and actually a big thing where the machine learning world meet and the software engineer meets is when the model, some sort of model, like statistical model, has to be exposed as a service. So that's a ubiquitous and very common pattern. So Amazon, I think, they're kind of the pinnacle of this. Amazon, like how Amazon Web Services started, was Jeff Bezos said, I'm going to make sure I have an edict down from the company that says everybody within the next, whatever it was, like 6 months to a year, better expose all their services only as JSON, or only as like some intercommunication. Nobody can directly import the other guy's service. Everything has to be a microservice. That's what created Amazon Web Services, believe it or not, out of nowhere, right? So that's actually what drives most data today. Data centers are all data scientists. So, for example, in data centers, one problem I help solve is something called preventative maintenance, where what we do is we pay attention to the sensors on servers, and then we say, OK, is it overheating? Is it going to die? What's the current hard drive? What's the current like hard drive space, right? And we detect when systems are about to die. So what we're able to do is we're actually able to salvage broken systems, and we're actually able to control when things die. So we're actually able to do controlled shutdowns of things we think are going to go wrong. This way they don't go wrong unpredictably. You send some stuff preemptively, and you prevent it from breaking. Another one is car sensors. So let's just say, so this is, sorry, oh yeah, yeah, thanks. So let's just say you listen to your car. You drop a mic in there, and you listen to the engine. And the engine starts, so let's just say you have it in there a few months, your engine starts sputtering. That's probably a problem. You're not gonna hear that though. But the mic will pick up like the most kind of nuanced anomaly, and it's gonna send a signal and say, oh, my engine's about to die. You don't know this, but you should go to a mechanic before it goes completely foobar, right? So if we think about it, a lot of data-oriented products or a lot of revenue actually comes from saying, I have some problem, and I want to monitor this thing, and this thing is core to my revenue, whatever it may be. That involves hooking up something that emits data, whether it's a customer service form. Let's just say you have a web app. Your web app generates data, right? That's all JSON blobs that all get stored in some database, Cassandra, Postgres, right? HBase. You know, that all gets stored in some SQL store, some data structure, or some database, and then somebody does something with that data. You don't hear about it after you guys store it. You don't hear about it again. You just know that basically these endpoints need to be here. Somebody asked for that. That somebody was on the other side of the table, being like, we have these metrics, and I'm trying to optimize for 50% more profit because I clicked the green button. That guy on the other side is the data scientist. So whenever you develop some end service, it's either core to the product or has some revenue stream attached to it, or maybe loss prevention, right? So maybe you want to de-risk or minimize loss, right? So a lot of that actually involves REST APIs, streaming analytics, data infrastructure. So you as kind of the software engineer are actually integral to the whole process. So you guys are what drive the actual data economy, because you guys are the ones that actually built the infrastructure for us to be able to do it in the first place. And those systems are powered by Java, which I guess is kind of the takeaway here. Those systems are powered by Java, and Java powers both the REST side of it, as well as the storage. Cassandra, written in Java. HBase, written in Java, right? So a lot of significant database, Hive, written in Java, right? You know, a lot of these storage systems are written in Java, and the web services that control them are also written in Java. Whether it's Dropwizard, Spring Boot, some sort of like, if you guys did like JBoss, or you did Glassfish, or you know the J2EE world, like a lot of those things actually a lot of those JVM-based systems actually connect to Hadoop. The JBoss developer has no idea what Hadoop is though. It's kind of a shame, because in reality it's the same language, and it's not really that much different. Like a Hadoop MapReduce job still uses generics that the web service developer uses for their abstract or their entity mapper or whatever of a certain type. It's all the same language. And in reality, it's also part of the same big system that's all driving the company. So kind of what I'm stressing here is the software engineer actually understanding the data side of things gives you more power and control over the stack. It allows you to actually understand, well, you know, in this case, I know that the other guy is going to need to do X, Y, and Z. So it allows you to kind of architect better systems. So at the very minimum, if you just want to keep being a software engineer, maybe just understanding a different part of the problem in the same space actually requires minimal effort and actually gives you a lot of upside, right? So that being said, machine learning, what exactly is it? So you have some observations. So for example, maybe the observations, so this is kind of abstract, but maybe the observations are a picture. And I want to count the number of people in the room. The observations are pixels. Maybe if I'm trying to predict housing prices, so in this case that's called regression, you know, based on the number of rooms, the number of floors, right? I want to predict what is the price of this house going to be in 5 years based on the price movement, right? So that's regression. There's labeling stuff. So how many people, like, is this a horse or is it a dog, right? So labeling things is another typical example. Another one, is the customer going to churn or not? Are they a big spender, yes or no? Is this spam or not spam, right? Clustering. So clustering I will just show a picture of because it's basically grouping things based on inherent trends in the data. When you see it, you'll recognize it, but you typically see it as a visualization. So regression, basically, what I'm going to do, there's two things I'm going to do here. I want to introduce the idea of regression from the machine learning perspective, because the things that are applicable to regression are applicable to the rest of machine learning. So you have some, so for example, you have some coefficient, a beta, if you guys have ever did regression, and that's something you optimize to get out a result. That's multiplied by some input. So that input is actually n-dimensional, and it's called a feature vector. So that feature vector is, for example, the number of rooms, the number of floors, the number of bathrooms, 0 or 1 if it has a master bathroom or not, right? That's a feature vector. So all those things then get set to some solution, like set to some price, and then you basically fit a line, right? That's actually all machine learning. You're fitting lines. You're fitting lines to data points. That's all it really is in disguise. So a feature vector is just a really fancy name for a set of observations about some example. So an individual example is an n-dimensional data point. Don't be scared of n dimensions. It's actually not that bad. It's just, think of it like observations. Rooms plus floors plus master bathroom. That's three random variables. So a feature vector is actually a set of what are called random variables. So a random variable in statistics is basically something that takes on a discrete or continuous set of values, has a range of values. That's all it is. So you have 3 random variables, right? And then that all gets set to some solution. So you have some end goal, and some data scientists probably came up with the metrics. Like, I know this matters the most. This is what analysts do. Analysts do something called feature engineering. Feature engineering is, they're usually a specialist. Whether they're a real estate analyst or they're fraud analyst. They know the trends in the data because all they do is explore data. That's all they do. So those people are very good at their jobs. They might not know much about software though. If they knew just a bit about software, they would actually be able to run better simulations themselves though. So there's always some coding involved here though. That's kind of litmus test. There's always some coding involved. And eventually, this will get integrated into some product at some point. You don't know. Go ahead. Sure. Can I? Sure. Can I draw it out? That's okay. Cool. Okay. Is the camera going to be able to? Where will the camera catch us? Over here? Okay. Great. Well, so the coding here. So you kind of have two sides. So you have the data scientist. And let's just say you're doing fraud prediction. Then you have the other side, which is, let's just say, the website that generates data. The fraud analyst inputs data that gets kind of used from the website. So the website was coded in something, and it kind of generates the data. So basically, what happens is you have a website that generates data that gets stored into a database. By the way, I'm going to go more in depth with a few more examples. I'm going to be hitting you with this over and over again. So I'm going to do a cursory example here just to kind of get like a baseline explanation, and then we can kind of expand as necessary. You'll see why I rushed through the software engineering section now. Anyways. So website generates data. This was coded up, and there was some storage logic, and you generate the database. That the fraud analysts connect to with SQL. So kind of the coding portion is in both ETL, as well as on the fraud side, which is Python and R. Maybe it's Hadoop and Spark, some machine learning library. It is actually actually, it's always a library that they're using. So in this case, like every machine learning library takes in a set of features that you encode as some sort of vector. So a lot of that is actually taking kind of like the raw SQL and converting it into a feature vector. This is called vectorization. So it's in building the models, connecting to the database, and outputting some model. And then that model is typically coded in a library. So that model has like an instance of linear regression. So linear regression, that was coded by some machine learning engineer somewhere who wrote that algorithm. So that some scientist wrote that algorithm. And then the data scientist is kind of the end user who knows how to feed data into the machine learning algorithm to get output out. So there's kind of two sides to the coding. There's the ETL side and the production stack that generates data. And then there's this joint data store where basically some guy on the product side wrote the ETL, and then some analyst is then using SQL or Python to kind of get the data out and then vectorize it in some form to build a model. And that model is then coded in Python or R typically, or productionized on Hadoop depending on how far you go with it. Does that make sense? Mm-hmm. Well, so a lot of I'm going to go into data. I'm actually going to be, the reason I'm going high level now is because I'm going to go in depth with data pipelines here in a bit, and that's going to be where a lot of the kind of the overlap in magic is, where I'm going to gradually kind of uncover. I'm going to start by lying to you, and then I'm going to gradually tell you the truth. That makes sense. So that being said, so what I want to do is make sure that we cover like at least the basic categories of machine learning, and then we'll kind of go into data pipelines and how all that ties back to solving problems. What I want to do is make sure that we understand why we're talking about machine learning first, though, and kind of like the different tasks. If you get a takeaway of this is machine learning, I've done my job. Beyond that, think about it from a software engineer's perspective. There's some data that needs to be analyzed, and machine learning is kind of the thing that does pattern recognition. If that's all you take away from this, great. Anyways, so now you have kind of classification. So if you're Zynga, you want to know who the big spenders are, right? So you, based on patterns in behavior, you want to figure out, and that game was coded in something, so it could be PHP, or it's like JavaScript maybe. It's something that generates data, right? So if you want to do user behavior prediction, and you want to say, the fact that they typically on average buy $100 worth of items a day, that's probably a big spender, because that individual service, or maybe like app, maybe it's in-app purchases. Mobile apps also generate data, right? So if you want to predict who the big spenders are, you log the transactions, and you say, on average, they've sustainably bought $50 a month worth of in-app purchases. That could be a big spender for you. It depends on, I think, on the game and what you charge, but that's going to typically be a big spender. So you want to target these people with free offers. Spend an extra $5, right? You want to be able to target those people. That's extra monetization. That's actually where data comes in, is in kind of extra monetization and targeting of users. That's for consumer. If you're doing enterprise might be risk mitigation, or it might, so in this case, like fraud or not fraud, spam or not spam. If you're doing email, for example, there's some email GUI, Gmail, IMAP, whatever, the protocol. And that was coded by some software engineer, some mailing server, some DevOps guy set up a mailing server that generates email, and it gives your end users or employees a way to send an email, and then that email can then be analyzed. And you want to know, what kind of email are they getting? Are they sending illicit messages out? Am I spamming people, right? And then from there, there's actually some ETL pipeline. So again, there's some text interface, and then this text is stored somewhere. And then if you want to do pattern recognition, you need to be able to, in this case, you need to be able to actually identify the words that are indicative of spam. So again, it's pattern detection, in this case, on text, right? Fraud or not fraud? Are they spending money? Are they throwing it away? Is the same IP trying to log into 10 different addresses? Right? Think about that for a second. So that's all based on weblog and Apache logs, right? So that's all stuff. I'm sure you guys are very familiar with Apache logs. So that's all. So that's all fraud or not fraud, right? You want to know when's the DDoS going to hit. If I'm getting if a page. So let's just say a page is being loaded once a minute from the same IP. That's not too bad. Once every 2 milliseconds, that's probably a bot, right? So the key takeaway here is some website or some product generates data, somebody analyzes it, and it's stored in a database. And then some pattern recognition, such as regression, to predict something like to predict the future, or classification to label something as yes or no. Those are both. That's all coding. There's all coding involved there. So as you can see, this is actually very production oriented, right? So from here, think about just one last example: churn prediction. So let's just say I know somebody's about to leave. Their spending's decreased over time, right? Think about that. You'll notice, my price is going down. And what I want to do is I want to evaluate whether I can save that user or not. Are they worth spending $5 on a free offer? That free offer that I want to target them with is an excuse to send them an email. I'm going to lose $5, but I might actually increase my lifetime value for that user, because if I give them $5, they're going to give me 15 back over 3 months.
Or just the cost of getting a user.
Right. Yep. Cost of acquisition. Mm-hmm.
And they found in the database they built, the real-time one.
Yep.
Using and SSDs from Intel.
Mm-hmm.
That they actually know certain customers.
Mm-hmm.
It's just worth more. Give them another phone, throw away $1 bill a year.
Right.
Than the $700 it costs to keep them.
Mm-hmm.
Yeah. So it's actually cheaper. Like, oh, your bill is $800. Like I had a startup one time.
Mm-hmm.
Probably easy.
Mm-hmm.
Oh, it was an $800 bill from roaming and putting PDFs down when you went to LA. Oh, no, we'll just throw it away. It's easier to keep you than actually get another customer.
Mm-hmm.
Yeah. Cart retention is the same. Everybody's doing cart retention now. The minute you sign in and you put something in your cart and then you ditch your cart, watch your email in 10 minutes, you're going to get an email saying $5 off on that Amazon book if you buy it now. Yeah.
Mm-hmm.
Same thing with SMS. Like you can even do SMS because we found that notifications has a higher ROI and quick return. Yeah.
Exactly. Yeah. See? All of a sudden, this big data and analytics stuff isn't all hype. It's actually practical. It's not all Hadoop, but there's actually real value.
Yeah, and Hadoop actually in HBase and all that stuff, it has to get its dependability stuff.
Mm-hmm.
Uber for Spark 2 weeks ago, they finally decided to do things like optimize the pipeline for
Yep.
getting data in and balance out the resources. So maybe it's not 45 minutes.
Yep.
Or whatever. It actually is 30. I'm like, dude, you guys are never going to beat the guys from Neo4j and others.
Right. Exactly.
Yeah.
Mm-hmm. You'll love my discussion later. We actually get into why software and hardware and data meet and why it matters.
GM stuff, right?
Mm-hmm.
That's what I'm here. I literally left the Tube Mobile event for machine learning 6 days.
Gotcha. Awesome. All right. Well, okay. So these systems, though, that generate this data are all built in Java, usually. These production stacks that you see are typically usually built and optimized in Java, where it's Spring, Drop Wizard, or some web service. And so you're trying to do some goal. Last thing, clustering. So this is clustering. So clustering is something called unsupervised learning. So unsupervised learning is just the ability to, based on statistics, the mean, maybe it's just the moving mean of the different data points, of their individual coordinates, and you automatically basically group data points based on their latent patterns in the data, and you identify subgroups. So, for example, this would be. So one algorithm that does this is something called k-means clustering. K-means clustering, all it does is it identifies the mean data points and figures out where should these centroids be. So the centroids, basically, they start random, and it moves everything around until it kind of identifies this is a centroid here, this is another one, this is another one, this is another one. And it basically figures out latent patterns in the data and where data actually gathers. So again, this is built, you don't have to understand the details of the algorithm, because I know like n-dimensional spaces kind of gets abstract, which is why I'm presenting it in a visual way. So we kind of know what clustering is, but we might not necessarily understand like all the details. Happy to get into as deep within the math as you want. I do, most of my day is actually calculus, but like at the end of the day, like the only thing you need to understand is that basically you have these data points and it automatically groups things based on latent trends in the data. So again, some production pipeline built this. So some production pipeline assembled all these data points. You ran a MapReduce job to compute all the means across all the different data points, right? You have some ETL pipeline, like you mentioned, like I want this to run in 15 minutes, not 30 or 45. I want to actually get results back fast, right? Or milliseconds if you're doing real-time streaming, or if you actually have the team to build that. A lot of people don't. Like I was addressing this earlier. Like, basically you have 3 levels of business. You start as a startup. You're Ruby on Rails. You don't know much. You don't even have data. You don't even know if you're going to survive tomorrow. Eventually, okay, this business thing worked. Let's grow to 15 to 40 people. Okay, now we'll think about scale. Now we'll think about like really building out a data pipeline. Now we'll start thinking about data. So now I'm going to hire some data engineers. Those data engineers are going to build kind of my data warehouse and my data infrastructure. They're going to assess what are my storage needs, what are my hardware needs, that kind of stuff. And then eventually you get to a big company where you start deploying microservices and some of these other things. And the architecture gets more complex over time. Yep. Or is it PaaS or not PaaS? Is it infrastructure as a service or not? Are you using Docker or are you using OpenShift or Cloud Foundry? Right? So so there's a lot of infrastructure decisions that kind of go into that. So what I want to do is kind of get into the data science workflow. So this is just a neat kind of Dilbert comic. Let us pray to big data. It's kind of right. So your manager, the takeaway here is your manager comes to you with some problem, right? So they have no idea how data works. They just know that their boss told them we need to optimize profits, and this is how we make money. Okay, data scientist, you figure it out because I'm your boss, right? So they might not know much. They have a spec sheet they were given by somebody else, and they're going to ask you a question. They don't know the results, but they need some intelligence. How many users are we retaining month over month? That's an SQL query. Build me a fraud model, because we're losing users, and we notice that we've noticed some weird things in the data. We don't know what it is, but do pattern detection, right? Either way, your manager comes to you with some problem, and you need it solved. You don't know how, but it starts ambiguous. From there, you do something called exploratory data analysis. So you extract, transform, load. So extract, transform, load means cleaning the data, getting it and retrieving it from the database, maybe from your data warehouse. Or if you haven't figured out how to load the data, you do some assessment and figure out, if this is you first building your data infrastructure, what data do we need? What's our schema? That's actually all related to what you guys do on a daily basis. This is just the start of the process. Okay, now let's just say we know what our problem is. We know what data we need to collect. Let's wait a couple weeks. Okay, we got some data now. What do we do with it? Well, we need to homogenize it because users don't know how to enter in data properly. Maybe the front-end developer missed some validation, so the zip codes are off. So I want them all in one format, right? These are all actually, again, highly practical things. This is not academic at all. These are things, again, you think about on a daily basis. But this is just the start of the process. Now, okay, let's just say my data is clean now. So now I have it all in a homogenized form, and I can start to do some sort of pattern detection on it, right? Okay, now let's normalize the data. And normalizing the data might be more than just cleaning it. It could be like, exploiting statistics and subtracting means and dividing by the standard deviation, right? Getting your data all between 0 and 1, so your machine learning algorithm can actually learn something. From there, after you've kind of visualized the data or scaled the data, you visualize it. So visualizing the data is kind of like clustering, what I mentioned earlier, right? Where you just group the data and you see what's here. I don't know. Like, is there any sort of decision boundary to be made here or not, right? For example, so let's just say this is my data. So I loaded it all in. I'm visualizing it now, and I want to know how many distinct. If I'm doing a classification problem, how many labels are there? Do I know? How can I figure that out? You can actually visualize the data and understand, oh, there's actually 4 distinct patterns that are picked up in the data. Now, let me do classification and say this is a 4 label problem because there's 4 clusters. So what you can do is you can teach a supervised learning algorithm being classification or regression, some target, 1, 2, 3, 4, right, to kind of automatically pick up this trend. So that's called supervised learning. So how do you do that? Mechanical Turk is a great example. So that's actually how a lot of supervised learning is done. Is you kind of outsource a lot of the data labeling to Mechanical Turk, or maybe if you're social network, your users label the data for you. Okay, congratulations. That's how consumer startups make money. They give it away, and then they have the users basically be a glorified data mining. The users help the social network data mine them, right? So the users are your outsourced kind of labeling database, right?
Especially Twitter with hashtags.
Oh yeah, Twitter with hashtags is a big one. Facebook search, Facebook, or even just click logs for these different websites. Pinterest is another great example of this. They actually have the biggest interest graph in the world. The boards, the names of the boards. Yeah, so they actually have an asset most people don't, which is really interesting. Quora is trying to figure out how to capture that kind of stuff, I believe, with topic modeling, actually. They're trying to figure out what people are interested in, right? So it all comes down to visualizing the data. And from there, now let's actually figure out, okay, did I have a problem? Or am I a data scientist and I need to come up with an excuse to justify my existence? So you explore so you're like, I'm going to explore some data. I don't know what I'm going to come up with, but it's awesome. Hey, but that happens. Like, that's why data scientist jobs are always so ambiguous, because this is where a lot of hype from big data comes from. There's value to be made here, whether it's based on some hype or some actual, we know we should be doing this, but some problem scope was created, and now I need to determine what problem I'm solving, or can I solve it? So, let's just say this data is completely noisy. Like, there's no trend here. I discovered that during the exploratory data analysis phase, right? So I know for a fact that there's no trends, and I should be trying to solve the problem in a different way. So maybe what I need to do is go back. Wait, where was it? And maybe I need to go back and renormalize the data. So maybe 0 to 1 didn't identify any patterns, but if I do -1 to 1, or I transform it and manipulate it in some way. This is what I was talking about earlier with data scientists. Data scientists are good liars, because if they know how to transform the data, they can find a good decision boundary that actually allows you to kind of separate the data and actually find some sort of patterns. This is why data scientists and statisticians are good liars, because you actually have to legitimately manipulate the data in your job in order to actually find any sort of patterns that you can then take advantage of. So this all comes back to, let's see, kind of diverting risk to making profits to making decisions. Maybe even just design decisions, right? You need to find some trend. You need to figure out, what are the observations I should be thinking about, right? All right, so what do we?
That's where the quote lies, and damn statistics come from.
There you go. Exactly. Exactly. So that being said, kind of the parallels to software engineering now. So both have a life cycle to follow. Like, you follow different stages. You have different stages of the business. Do I need a data scientist right now or not? So if we go back to this, kind of these 3 phases, here you're not worried about scale, and you also don't have a data science team. You might not even have data, right? So you move fast, break things. You don't have a statically typed system, and you don't have a big code base yet. Eventually, you figured out, oh, I seem to have this startup. A startup is what we call a happen to be incorporated entity that's searching for a business model. After we figured out if this thing's going to survive or not, then we're worried about growing the company from 15 employees to 100, which that involves data infrastructure, and actually, like, what we'll call is kind of like cranking the wheel now. Let's actually figure out where the profits are. That's when you might actually start building kind of a data storage system, right? So then eventually you kind of, then again, you kind of get into this advanced ETL stage where now you need to worry about, what kind of data am I dealing with, and where are the profit centers? So throughout this whole lecture, we've seen that everything's actually a pipeline. So everything involves some sort of goal, a product that you're building, where you collect data, you set up the database. So this is the second part of the company. You set up the database, and now I basically want to hire a team and solve some problems. This all involves pipelines of some kind, right? This all involves some sort of production system where it's core to the business. In reality, this is usually made up of two teams. The software engineer, understanding a larger component of the business, though, allows them to figure out where are the profit centers, because that's what the data scientist predicts. The data scientist predicts where the profit centers are.
Wouldn't the ops team though kind of tell you a lot of this because they're looking at statistics on how the business is run?
Well, that's
Cost centers, where the ROI is.
so that's an analytics team, right? So that's they call themselves data scientists too. So it really varies. Like I addressed this at the beginning, where a lot of the in this case the ops team does a different kind of data analysis. They figure, like, if you're doing DevOps, they look at click logs, right?
More than that, I'm actually saying that we do a lot more than that. We go through what you do, real ops team look at the whole enterprise software or web-based company. They look at everything. So that's really where you come.
So define operations, because there's DevOps, there's like operations staff. Right. Right. So logistics operations. So when I think of operations, I think of IT operations. But you're absolutely right. So operations people are typically analysts then, yes. So they're doing some sort of data analysis, and they're figuring out what should we be focusing on. Like so why Tim Cook's CEO of Apple? He was the CEO. Apple's actual asset was not, like, their computers are great, but why they're profitable is because they actually secured one of the best logistics pipelines in the world. And they actually figured out where are our profit centers and who do we secure relationships with early.
Yeah, he literally figured out how to rent the bottom floors of all the planes at
Right.
a flat rate. That's why he's CEO. He saved so much money on that.
Right.
And he should be chairman now. And Elon should be CEO.
They need a visionary, for sure. But the key thing here is you have software engineering, and it's touching some data. And now and then you kind of you kind of have two sides to this. So where does that sort of play in then? So we know sort of why to care about this. But the key thing here is that machine learning is integrated into software. Machine learning models are written in machine learning libraries. Your regression algorithm, your stats distribution, that was implemented by some scientist. And it's typically written in Python. Maybe it's Java. I wish, so you have a lot of, so Spark is kind of helping this a bit because it's a little bit easier to do machine learning in, right? But it's often a second, so like a lot of these, so this side though, they have to touch code, but these people care about production systems. These guys are just worried about the prototype. So they only think about the math. When in reality though, it all affects the same system. And the stronger your team is on the data side, the easier it is for them to actually build and think about the overall product, and therefore increase not only productivity, but also profitability. So the thing here is data scientists don't often think about production. So that being said, ML software. So this is kind of where we get into kind of the rabbit hole now. So we've talked about regression, classification, and clustering. So those are all categories of algorithms that have software written with them, which includes like Hadoop, includes Spark. If we think about, for example, we think about Mahout. So we got Mahout, MLlib, right? These are kind of the canonical, Hadoop and JVM-based ecosystem libraries that we're seeing today. So those both have clustering algorithms. So these clustering algorithms run on your data. You can load something from Cassandra. You build something called an RDD. And that RDD or maybe MapReduce job if you're doing Hadoop does some sort of machine learning. So you can do machine learning directly on your data in Java. All of a sudden, it's not too bad. This is all then connected to a production stack. So maybe you're just using elastic MapReduce. You can still run distributed machine learning on top of that though, but that's written in Java. So Java is close to the profit center. It's where data is stored. Your database is written in Java, right? Your website might be written in Java, and then that connects to a JVM-based solution for machine learning written in Java, right? So all of a sudden, the end-to-end stack makes sense. So there's a problem here, though, that might not be obvious immediately, and it's that these machine learning libraries typically have the ETL built into them. They're not modular. So this is kind of the punchline. A lot of these machine learning libraries today, because they're built by scientists who don't think about production, so therefore they're not modular. So you have these guys who happen to know distributed machine learning building stuff for these guys. There's kind of this mismatch. Some guys do it right. Not all the libraries are crap, but there's definitely some misconceptions about scalability as well. But flexibility is not something they think about.
Literally was just at the Spark meetup 2 months ago.
Yep.
The discussion, you should see the post. This is exactly why Spark 2, they're literally like, we need to build modules that manage like the Spark data flow coming in, because the faster the data comes in,
Yep.
the slower it actually mines it. I'm like, yeah, I'm a Cisco guy, didn't you think about it in the first place? Didn't you see the whole thing we did with OpenStack and building this stuff for JavaScript and like
Nope.
HTML5 have sockets and SQLite and local storage and processing and distribute that problem modularly?
No, nobody. So that's the thing. Like the Spark guys didn't think about that at all, actually. So nobody in practice. And I haven't seen this in years now. Some people still use it for certain things. I know like some people I think are using it for maybe recommendation engines. But in general, like a lot of people I know are moving. These guys are trying to rewrite it in Scala and do some other fun stuff. But key point here, a lot of it's happening in Spark today, or actually people handwrite their own machine learning. So what I actually see in production is a lot of people writing their own distributed machine learning. So I know like a lot of the banks do this. So they typically write their own Java-based machine learning, maybe on top of Hadoop or Spark. They might not use the libraries because they were built wrong, right? So and then basically they build these machine learning libraries for their particular problem. Like they build a really fast fraud detection system, and then they make the algorithms modular. No, they probably don't. So they don't have an incentive to typically. So a lot of these things are still built. A lot of these things are still built wrong. They're still built in a way that doesn't allow you to cleanly separate and run the algorithm in different places. So
Startup ML, like I literally after meeting
right.
one of the boys, he went back to contributing to MIT and at Tufts doing some crazy stuff for biotech.
Yep.
Literally, they're like, yeah, half of our customers are hedge funds, startup.ml. The other
Yep.
ones are all startups.
Yep.
So they're starting to come to ability to plug and play this stuff. There's open source projects coming out for some of the problems. The Spark streaming stuff is where all the really hardcore cool stuff's coming. The guys at startup.ml are ex-Yelp fraud guys.
Oh yeah.
Yeah, so.
For sure. Well, and that's the thing. But even then, Spark streaming is actually still a horrible architected application
Yeah.
because
They're like,
because
yeah, Spark was old school.
right.
If they're not running Bigtable and Next Google other stuff, then they're all
Spark, right. So they're doing, but typically Spark streaming even then is still pseudo mini batch, which is why you have Flink and some of these other things as well. There's always going to be a new big data project, whatever, technology evolves. Key point here though, like a lot of machine, like this wouldn't be hard to get right though. The standards for machine learning, it wouldn't be that hard to raise the bar even just a little bit. So that's a lot of what I spend my time on actually. So in this case, let's just think about the components. So key thing here is ETL and vectorization. So let's ingest the data from SQL, from S3, from my routers, right? From different data sources. Let's bring it all together in a data warehouse, and then let's turn it into some feature vector for a model. That's its own problem. That should be handled by the software engineers. The data scientists should just tell them what they need, the observations they need. So again, a feature vector, just a set of observations. And then the software engineers should build these vectorization pipelines. And then from there, we should have something separate that actually manipulates the data. So you don't want to manipulate your data. Like you want to keep your data as clean as possible in raw form. You want it clean and you want it pristine, and you don't want to manipulate it. But data is good in certain forms for certain problems. So normalizing the data between 0 and 1 is something that should be done at a massive scale. And it should be stored separately from the original pristine data so people can reuse it in multiple locations. Right? So this is what a real production ML system looks like. Then you get into data exploration. So now this infrastructure should be different from this infrastructure. So when you get into data exploration, that's when you get into, OK, now how do I want to visualize this? And where do I get the data to visualize? Right? These are all separate concerns. Eventually, we get into model building. So now after we've explored the data, I've manipulated it in a form that makes sense for me to do machine learning on. OK, now let me build my model. Let me group it in some way. Let me do regression. Let me solve whatever my end goal is. Maybe it's just A/B testing. Right? And then after I get into my model building, now we get into the Lambda architecture. So now we get into streaming. So now my model is actually serving requests and updating in real time. So this is kind of the pinnacle. These are all separate systems, though. Like, the model should be separate from the model serving system. The model serving system should be separate from the data exploration. And the reason for that, if anything else, is you want to be able to plug and play different models. So if you think about it, what if I want 10 models? I don't want to build one model integration system and then not be able to plug in more models, right? What if I want things to be optional? And the reason for that is you never know when you're going to update. And a lot of these decisions aren't hard to make up front. If you're able to say, just let me just design this to be able to plug in a model. Like, it's not a hard decision to make and saves a lot of technical debt long term. Right now, if you look at like what happens in a lot of distributed machine learning, the vectorization is built in with the model build. Model evaluation as well. All these things are built into one library. But the concepts are cross-platform across several different verticals.
A lot of it is religious. Like, this was a part of the presentation you just
Yep.
from the one about machine learning for groups that don't have data to train off the beginning. Like,
Yep.
take things from other data sets.
Exactly, and aggregate them, and right.
Because people will take, there may be neural networks, and they combine it with this and that, and they're religious about that.
That's an ensemble.
Yeah.
Exactly. So.
And really, it should be modular.
And yeah, exactly. And that's right. And that's the thing. Most production ML systems are based on ensembles. That's what real systems are. They're all based on ensembles. So there's always multiple models involved. The way these libraries are built, though, and this is what Spark was trying to address with Spark ML, is the ability to kind of compose models and build like an overall pipeline where you use several different models and then you like average the result of the models, right? So, but the thing you need to be able to do, though, especially in data, is experiment. You want experimentation to be fast. You want evaluation to be fast. And if you architect it right from the get-go, with the right software engineering concerns, then this process doesn't have to take a year. This process can take minutes. If you build it right and automate it the first time, this is something you should be thinking about up front. The thing about data is that if you're doing data analysis, you have a team. And that team is going to involve communications. It's going to involve a lot of code. And there's probably going to be a lot of technical debt up front that you're going to have to deal with. So by the time you get to this point, you will have the resources to be able to handle these kinds of problems. And there's really no excuse you shouldn't be building it right up front. There's a lot of open source software out there. It just needs to be composed differently. So that being said, for example, for vectorization, Spark, for example, only allows you to read like 1 or 2 formats maybe. And they can't even deal with binary data. They can't do images. They can't do weblogs. They can't do text. Right? They're sort of starting to, but it's very limited at best. Spark can maybe handle English as far as text goes, but beyond that, God forbid the international audience, right? Data manipulation, like Spark does everything in memory. In reality, like you're running out of RAM, right? So there's kind of this middle ground you need to be hitting, right? But you need to be able to. So if you're doing a lot with Spark, you typically need to set partitions. They got this right with data frames. Data frames handle the partitions for you, but even then, you still end up with a lot of problems. These are all still separate concerns you should be thinking about, though. So if you can think about, OK, how do we address what problems do we have? What do I need to load? Where do I need to store it? What data structures are best for manipulating the data? And then what is a system I can use to export? This is probably some web interface that talks to this. So maybe you manipulate it from your web UI, right? And then from there, it's like, OK, now what am I going to plug in for my models? What kind of models should I be using? There's probably going to be several. So if you have a recommendation engine, the recommendation engine is probably going to load data from several different places, going to be manipulated in different ways depending on the domain where it came from, and then you're going to want to explore it in one unified interface that you can then use to build a model. All of a sudden, this isn't so crackpotish anymore. Like, it's, you know, if you already have the resources, which you will if you're doing this, because if this is worth your time, you should already be doing this, right? Or you should be thinking about how to build these systems. And then from there, you get finally to the, again to the end where you're kind of, now it's like, now let's do real-time recommendations, right? And this is kind of where ML architectures are evolving to. Not a lot of companies have this yet. They want to, and they're starting to move towards this, but people are only just now starting to realize streaming is actually important. I should be able to update my models in real time. There's no reason we can't do failover and then put the old model offline and update it, right? You know, that should be seamless. That should be handled by a library. But it should be the point that these systems exist and that they're possible now. Yep.
Platform, you go into your AWS company with the SSD drive, your Intel stuff there, you're in the millisecond world.
Right.
You can do it.
Low latency.
Yeah.
Low latency stuff. Exactly. So now, it's cheap. Exactly. Yep. Storage is cheap now. Well, so that's the thing. Data storage is cheap now. So key thing here though, models should run on different platforms, even on your phone. Spark doesn't run on your phone. You're like, what? Okay. What I'm getting here is edge devices. So as we get, throughout the coming years, we have routers now. We're going to have iBeacons. We're going to have increasing amounts of sensors. And phones get more powerful. Like the next Samsung phone is going to have 6 gigs of RAM. Who's going to know what to do with 6 gigs of RAM in a Samsung phone?
People buy 32, 64 gig RAM. So
right.
That's what H.1.5 is. Like you can actually, that's why Dart runs its own VM with protected threads.
Right.
So with an SSD drive, which in H.1.5 standard is supposed to go to 5 or 50 megabytes,
Mm-hmm.
web page is running 5,500 megabytes per page, per different page.
Right. Yep.
5 to 10 sockets. If you want to see the performance on this, look at the stuff that Steve's Solders is doing over at Fastly after he left Google.
Yep.
Basically, this is a server node.
It's a server node. Yes.
4G LTE connection. It's got
Yep.
gigs to tens of gigs of RAM. Most people have a 20
Yep.
or 32 gig chip.
Yep.
It's got 5 to 1 microsecond read writes. Look at what
Yep.
PlayStation did with OpenGL.
Yep.
You actually have
A supercomputer.
server.
Yes.
And it does redundancy without master slaves around the edge. So it can talk to other users if you instantiate it, and then
Right.
update you after it does
Peer-to-peer.
the hard work of processing the data for you for free.
There you go. Yep. Exactly.
Yeah.
So edge devices are going to become more prominent in the next few years. So there's no reason that machine learning model, that machine learning model in practice is actually small enough to run just right on your phone. You don't need a network connection. They're not going to, the MLlib guys aren't going to tell you that. They're going to want you to stay in the cloud, on the server, with their, right. They're not going to tell you that. So my play in this space, so kind of, this is kind of how I built, so I primarily work with unstructured data, but I wrote hardware that's swappable with a scientific library that's a DSL for matrix math that runs on the GPU, OpenCL, Intel MKL, a lot of the different ARM architectures. So what I did was I actually made software or hardware a microservice. So I took hardware and abstracted it away, and I actually made it a microservice. So my algorithms don't know about my matrix math. They just know I want to do 2 plus 2. It doesn't care what chip it's on. This library takes care of that. The algorithms are then written in the thing that handles the hardware. And then that, in turn, has basically the algorithms are isolated from the distributed runtime. So or the phone. So one of our biggest actual platform is we have hybrid models that run on Android, as well as on the phone, or as well as on the server in Hadoop and Spark, with no internet connection. So we can actually deploy models as APKs. So I'm not focused only on the cloud anymore. I'm actually focused on edge devices. And the reason for that is unstructured data. Sensors are all generated on Android-based sensor devices, phone-based in a lot of phones as well. Yep, RFID. Yep, there you go. Okay, so that's so.
So you build SETI at home for IoT.
Yeah.
So just to clarify what you're saying, right?
Mm-hmm.
So the stuff that's running on Hadoop, Spark, or whatever, I mean, that's the actual bit that's doing the learning.
Well, and that's the thing. You can then export that to the phone.
Okay, so I mean, there's two. Kind of want to make a distinction between that code and then the model that it produces.
Well, both. It's actually the exact same code.
But then that model then runs on.
Yep.
Could run on phone.
Yep. And so you can actually use the same Java-based workflow and then deploy it as an APK or as a Spark jar. So the exact same code, 0 lines changed, just different hardware deployed. So maybe you're running an ARM optimized on your phone, ARM optimized matrices on your phone, and CUDA optimized on your server, because NVIDIA doesn't actually have traction on mobile, but so you want to optimize for different architectures. But math should be cross-platform. Math should not be something I think about. I shouldn't have to worry about what chip I'm optimizing on. My software should do that for me, and it should be open source, which is kind of that was kind of my opinion on this. And then the models shouldn't care what chip they're running on, or what runtime they're running on. I should be able to say DL4j train on Spark hardware GPUs, or maybe if ND4j does it right, which we do, we actually do hardware discovery and we figure out if you include multiple backends, we figure out, are you running CUDA, are you running OpenCL, what are you running, and then if it's available, we'll run whatever you have on the phone or on the server, and then so you can have one Jenkins instance that outputs a jar file for Android and a jar file for your Spark jobs, and it's all the same code. And then we have an ETL pipeline called Canova, so we actually separated out loading an image. This should be a separate unit test from my machine learning. So if I have my own custom ETL, I should be able to plug this in. If I want to optimize on a particular chip, I should be able to plug that in, right? And I should be able to make it run everywhere. The algorithms themselves should run on mobile or cloud. They should run in your Hadoop cluster or on your Android phone. The concept of a neural net, I shouldn't care where a neural net runs. If the neural net is small in practice, but is trained on a cluster because it's computationally intensive, I should still be able to benefit from that thing on my phone. And I shouldn't have to write a new line of code to do it. And then from there, then you have your predictions and classifications, and it's all the exact same code. So ETL pipelines, swappable with hardware, swappable with distributed runtime or phone. So everything is swappable, including model evaluation and everything else. So in this case, for example, we actually have Spark examples where I use MLlib's evaluation metrics instead of our own, and then I show that basically we can speak Spark, and we just translate it for you, and then you can just use it. So we actually have Spark ML pipelines as well. So we're the only deep learning on Spark that support. Actually, we are the only deep learning on Spark, but deep learning on Spark that also supports Spark ML. So we actually have integrated Spark. We actually have a Spark package already that allows you to just use native Spark pipelines right in with your neural nets. So you can build an arbitrary neural net architecture like a convnet or a recursive convnet or whatever crazy architecture you want to build, and then you can make that run anywhere. So if there's any takeaway here, if you're doing regression, k-means, what have you, you can then apply the same. You can actually in ND4j, and we've had people do this. I actually have some guy at Amazon that did this with us. NASA used this as well, actually, for just some weather forecasting. But they used it as kind of like a cross-platform math library, and then they wrote their own algorithms. So you can actually just write. There's nothing stopping you from writing scikit-learn in ND4j. This is just NumPy. That's all it is. It's NumPy. It's R, right? So there's nothing stopping you from writing your own algorithms with just cross-platform math. So so academics can actually extend it the same way they know MATLAB. This is basically MATLAB in Java. So you can extend it the same way you know MATLAB and then plug it into Hadoop and Spark, because we actually have a distributed runtime that just knows what an algorithm is, and then you can run any algorithm. So key point here: machine learning should be swappable, and the trends over the next the next couple years here are going to move towards smarter devices that run things without an internet connection, because a lot of things are going to be kind of hybrid, online, offline. That's what we're going to see with IoT. Like fridges a lot of my customers, like, they don't want everything online all the time, and it's going to be spotty internet connections. So they want to occasionally pull in updates or what have you, but they want things to run locally, right? And things are powerful enough to where you can get to that point. So takeaway here is monolithic systems right now are still ML is still in its infancy in terms of software engineering practices, and over the next few years things are going to become more modular. And I think and there's going to be that's the thing. There's actually going to be real monetary drivers for that particular movement. So over the next few years, we're going to see software engineering practices in machine learning become better, and it's going to become more of a first-class citizen. And with that, thank you. All right, so I figured I'd leave like a little bit of breathing, like half hour or so for questions. Yep. I don't. I think as far as compilers go, LLVM would be the best bet for that. Like that's where because Apple has the most incentive, and Apple sponsors the project. They have the most incentives, I think, to make stuff fast. And LLVM is starting to be supported by Intel and all these other guys. So I think a lot of weight's going to be thrown behind Clang. But as far as VMs go, I'm actually a big believer in not having VMs and just having I'm actually a big believer in containers. Docker, yeah. So like or CoreOS or what have you, like Rocket. Like I'm a big believer in not having the overhead of VMs at all, if possible. But right, yeah, it's right. It's like, am I using Kubernetes? Am I using like Docker? Like, no, I get that, but I kind of just like, I'm more focused. Like right now, I think the compilers will be able to handle it. It's going to take time. You start to get into So my thoughts on this, like Dalvik and Art. Art is an improvement over Dalvik as far as VMs go. Yep. Oh yeah.
But they just need to make it SSD speed.
Right.
They have no real memory garbage collection for SSD drives.
Right.
Outside of the algorithmic trading guys.
Right.
Which are in the nano world, they'll never make it.
Exactly. Yeah, exactly. Well, I think that's what I think that's what the Zing JVM does. That's what certain commercial JVMs do, is they kind of implement that. And that's actually why I wrote it in Java, because I think like there will be incentives to write faster JVMs that will just run a lot of the legacy code that's been around for years. Like the JVM bytecode format itself, I've dealt a lot with just raw bytecode. I do a lot of code generation, and I found like it's not that bad. Like the JVM bytecode we're working with at a raw level. Like exactly. Yep. Exactly. So like a lot of our matrix operations are actually just in time. Mainly because like there's certain operations where if you unroll it, like the calculations are that much faster. It's literally milliseconds, which milliseconds times a million adds up. Especially if it's being called a million times a second, that millisecond if that 5 milliseconds can actually shave 10 seconds off your overall like prediction time, right? So a lot of this stuff, a lot of performance tuning adds up. And the takeaway here is hardware is going to become more and more important, especially depending on where it runs and like how it's optimized. So like, am I going to have an ARM JVM or am I going to have an x86 JVM, right? So that gets. Okay, so I'll be honest with you. I'm playing the whole space. So our biggest customers are Intel. We also work with ARM and Huawei. We work with NVIDIA. We do some, some other chip makers as well. And we're playing the whole space. I'm not picking a winner. NVIDIA. I think NVIDIA is going to end up. They're going to take a significant portion of the server market. Intel's going to try to dominate with what they have already. Maybe they're going to move to FPGAs because of Altera. Who knows? But right, and that's the thing. So nobody can really predict the future. I just know that chips are the way to go, and software should be thinking about hardware in some form. That's why we're starting to like, with the JVM, we're starting to like optimize off memory heaps and, pick the right garbage collection algorithm. Like there's a lot of like tuning and low latency things that actually have gone into the JVM.
What do you think about the stuff that I think people better watch Dart's isolates because you know who built it?
Right. That's
So
true.
I can say this because I'm not under the game with one, and we fund companies. But it was interesting that James Gosling went to Google right before the Oracle trial,
Yep.
and then Doplet came out, and
Yep.
Dart. No, Doplet was already out because he kicked their butt at Oracle.
Yep.
Then Dart came out with isolates and the compiler guys, and then he funded his own startup with no raise for $16 million.
Yep.
I'm sure in order to avoid paying Oracle $8 billion, they gave him a couple $100 million.
Yep.
I'm sure of that.
Oh yeah, for sure. Exactly. I mean, so the key takeaway is the JVM is actually it runs in a lot of places and is going to be optimized for hardware in the next few years. So there will be a lot of extra concerns to think about. Speed is going to become a necessity. Are you guys as end users going to deal with this? Maybe not, but you guys will sure get benefits from it. Because the JVM as JVM runs in more places, whether it's Android, whether it's edge devices, whether it's like sensors, Twitter, like wherever it runs, you guys will continue to benefit from it because there's a lot of innovation being done in that space, especially in numerical software. Any other questions? All right. Cool. All right. Thanks.